Yep, forgot to make that visible, didn't we? Yeah, we'll let it go. That's fine. All right, so CS 797K, Monday, February 10th, and we're going to talk now about the main lecture, which is ISBN and Galois fields. Remember from our course outline, we are talking about block-based protection, and we are starting to talk about complex Reed-Solomon coding. We're going to do a backup. We're going to do some finite field arithmetic and show you how that works. So this is kind of a theoretical lecture here. So RAID-DP works with doing XORs in two different directions, right? That's one way to get multiple different parities. We can't just calculate the same parity in the same method we did, just have an extra drive on the right side, because all we're doing is just duplicating the information that's already there, right? We have to find a way to store it such that it's not the same calculations. That's what I call an engineer solution. The engineer says, hey, if I can just make my XORs go a different direction, I can be higher reliability. Well, RAID 6 PQ parity is what we call the mathematician solution. And that is, instead of calculating a simple XOR parity, we calculate a different kind of parity. We calculate a parity inside a Galois field, a finite field, using what's called Reed-Solomon coding. Have you ever seen a compact disc, an audio compact disc, or a Blu-ray or a DVD? The coding on those uses Reed-Solomon coding. You can take, I wouldn't recommend doing it, but you can take a DVD and get a big old scratch, with a nail or something like that, and put it in your DVD player, your Blu-ray player, and it'll still play the movie with a huge scratch across it. The amount of damage that you can do to a DVD or a music video or music CD before it stops playing is really impressive, right? And of course, they knew that these things were going to get scratched up, and they knew that people were going to pay a lot of money for these, and they wanted to make it so that people could listen to their music without having to fear that they drop it on the floor. That was one of the notorious problems with old vinyl records, right? You'd play it long enough, it would start scratching and skipping, and things that just didn't fall apart. It would degrade slowly. So they wanted to prevent that from happening with CDs. So that's why they used Reed-Solomon coding, and RAID algorithms use that same coding system in some products. So in order to understand Galois algebra, finite field algebra, we're going to go back in our time machine to 1966 with the invention of what we call standard book numbering. So if you have a book, right, there's a number on the back of the book that encodes what that book is, right? Classically, before 1980 something or other, it was a 10-digit number. And that 10-digit number represented a Galois field of size 11. And that's actually an ISO standard from 1970. And that was based on the ISBN from 1966, where some British publishers came up with the notion of we need to find a way to track all these books and know which one's which, right? So in 2007, it was cut over permanently to the new 13-digit number, which is not a Galois field. It's a weaker checksum. It's got more digits. It allows more books. They needed to have bigger numbers because people are publishing a ton of books still. There was an overlap period between the 1980s and 2007 where you could see both. That's Beethoven, in case anybody wonders. It's my ringtone. Both formats are n digits plus a checksum digit, either 9-digit number of the book plus a checksum at the end, or a 12-digit number plus a checksum. We're going to focus on the 10-digit version because it's the Galois field. Here's some books that I stole from my bookshelf at home. Well, I took off my bookshelf. You can see here's the number 3-458-32135-7. That's the ISBN number. Here it is 0-394-75817-X. And here it also, this was in the interim period between the old and the new. This is the new version, 9780394758176. So it's got the 13-digit number up here too. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. That's still 11. There's a long number down here. 9781250151117-9. That's a 13-digit number down there. But we're going to focus on these old versions, 10-digit numbers. That's a 13-digit. What's that? Yeah. Yes. Is that this one here? Yeah. And X is a digit in ISBN. So yeah. You notice an X? Yeah, that's actually a digit, and that is a 13-digit number up here. That's the new version. You notice there's no X's in there because people complained about the X's. Yeah, especially people in data science classes or data storage, advanced topics in data storage. We got an imaginary conversation. Here's where I practice my fake British accent. We have an imaginary conversation between two booksellers in Britain, and we need a better way to track our book inventory. Well, says the second fellow, why don't we just assign every book a number? Obviously, but what if someone mistypes the number? Let's add a check digit at the end. Okay, how does that work? I suspect Brits don't actually say okay, do they? Like this. Here's, we'll call our ISBN, we'll say there's the first digit is the language. And then the next bit, 3 digits are the publisher, publishing house. And then we have a number for the book that's published. This is book number 775,599. And then we add a check digit. And we'll take each number and multiply it by the position that it's in. This is position 1, 0 times 1. Position 2, 2 times 3. So on and so forth. We'll multiply the check digit by 10. So 0, 6 plus 27 plus 16 plus 35 plus 30 plus 35 plus 72 plus 81. We take that modulus 11 to get back to our check bit. We get 302 mod 11. It gives us 5. So we put a 5 in that place. So the whole thing adds up to a multiple of 11. If I take that 352, 5 times 10 is 50, 352 mod 11, I get a 0, right? So I know that someone has typed in the number correctly in that case. So what good does that do? Well, suppose someone transposes 2 digits. My British accent there is terrible. Dealing with transpositions. Yes, that's a joke, transpositions. Yeah, the correct value is this. If someone types in the wrong values, or instead of typing in 7.5 in the middle, they type in 5.7, we do our multiplication, and we get, instead of 7 times 5 is 35, and 5 times 6 is 30, we get 25 and 42. We sum all those together, we get 354. We take 354 modulus 11, and it doesn't work out. It comes out to 2. So I know something went wrong in typing that number. Again, this is 1966. They're typing these in on cash registers or writing them down or whatever, right? They're not using scanning. They didn't have barcodes yet in 1966. Can you imagine living life without barcodes? Yeah, sure, why not? Not a problem. So you see, if someone gets a digit out of place, the checksum doesn't add up to a multiple of 11 anymore. Well, that's very nice. Can it correct the error? Not exactly. It can find a missing digit. If someone types it in and we get it wrong, this is an erasure code. This is why Galois fields are perfect for RAID. Remember we talked about SecDed code, single error detection, or single error correction, double error detection, where it can actually correct the error, versus RAID, where the algorithm is implemented to fix the data, recalculate the data that's on a missing drive. It's not wrong data, it's just gone. You know the data is not there, right? That's an erasure code. It handles erasures. So how do we correct a missing digit? Well, let's imagine that we've got our, typing this in, and we, typed in or wrote down the wrong number or something like this on our little piece of notepad paper, right? 0394, and I can't read what that digit is. 55995. What is that digit? Well, let's go ahead and do our math. 0 times 1, 3 times 2, 9 times 3, 4 times 4, splat times 5. We'll call that a 0. Let's assume it was a 0, right? 5 times 6, 5 times 7, so on and so forth. 317 mod 11 is 9. Therefore, algebra tells us that splat times 5 plus 9 must equal 0. If I had the right value in there, I'd multiply it by 5. I add it to the value that I have here, which is missing that value, and I should get a 0. So that means that splat is equal to minus 9 times 1/5, which is equal to 2 times 9, which is equal to 7. Minus 9 times 1/5 is equal to 2 times 9 is equal to 7. What? Ah, of course, you need this multiplication table right here. Times table over a Galois field of size 11, a finite field. If you have, multiplication in the real numbers, right, goes on infinitely in any direction. In a finite field, we limit it. Here's a field we've limited to size 11. We've got the numbers 0 through 10. That's all the digits we have. So we see 2 times 9 is 7, right? And 1 over 5 is 9. That table's wrong. 2 times 9 is 18, not 7. How about you see this times table is modulo 11? So any number that exceeds 11 gets chopped down until it fits. 18 mod 11, 7. What about 1/5 turning into 9? Well, you see, where 5 times 9 equals 1, that tells us they are multiplicative inverses. Multiplicative inverse, is this a joke? Angry British sounds, yeah, okay. Multiplicative inverse. Y is the multiplicative inverse of x if and only if x times y is equal to 1. In real numbers, 4/3 times 3/4 is 1. 5 times 1/5 is 1. 1 times 1 is 1, right? So the multiplicative inverse is just that number flipped upside down. Inside, in modular arithmetic over a prime number, there are no fractions. Everything is an integer. The inverse is an integer. The inverse of 1 is 1. The inverse of 2 is 6. The inverse of 3 is 4. The inverse of 4 is 3. The inverse of 5 is 9. 6 is 2. 7 is 8. 8 is 7. And 9 is 5. You notice that 5 and 9 and 9/5 they're reflecting, right? And the inverse of 10 is 10. Proof. 2 times 6 is 12. 12 modulus 11 is 1, right? 3 times 4 is also 12. 5 times 9 is 45. Modulus 11 is 1, right? 44. And 55 is just 1 less than 56. And 99 is 1 less than 100. So those are the multiplicative inverses. So try this. Find what splat is. So what does this x mean? It's the Roman numeral for 10, of course. Why didn't you just use A like proper hexadecimal? Because I'm a 1966 British bookseller, not a 21st century computer scientist. That's why. Okay, so x means, what do we say, 10, right? So here we go. Here's our exercise. First, you're going to go ahead and multiply all these numbers by the position. So what are our values going to be here? Right here is going to be 6, 27, 16, 7 times 5 is 35, 5 times 6, 30, 0, 8, 63, and 10 times 10 is 100, right? There we go. Now we sum all those together. Who wants to try and do it quickly? Anybody? Too late. I beat you to it. We add all those numbers up, we get 285. Now we take 285 modulus 11. What do you get? Surely you've got a calculator with modulus on it, right? You get 10. Yes, absolutely. 285% 11 is 10. So now splat times 7 plus 10 should equal 0. That's our equation. We do the rearranging using our algebra. We need to say that splat is minus 10 divided by 7 minus 10. We bring that using modulus arithmetic inside the field using, and becomes 1. So we're just looking for 1 divided by 7. So we go into our table. We find 7, either in this row or in this column. We find the 1. We read the other direction. We get 8, right? So 1/7 is 8. Therefore, the missing number is 8. As we see right there on the book, the value is 75817, right? We have some sources for you to look at if you're curious about more information. For instance, as I pointed out, they came up with a 13-digit one later, which is actually a much simpler code. If you care to read about it, you can. If you don't care, you can skip it. But the ISBN agency actually has its own website out there on the internet where it talks about international standard book numberings. There's a website out here where you can take these numbers that I've got on here, right? I've only showed you the back side of the book. Some of those books are humorous just because they got strange titles. So if you're curious to find out what the title of the book is, you can go up to this slide here, type in 0394 75817-X. Find that book. It's going. It'll eventually get there. One for the road, hitchhiking through the Australian outback. That's what you can check other books are too. So there's actually a full database. This fellow Terriveau, we'll see a lot of things on Richard Terriveau, University of New Brunswick. He has a page on ISBN where he does calculations, talks about how it works, talks about the 13-bit ISBN as well. One possible approach. He actually goes in to do a whole bunch of stuff on there for the 13-bit value, I think. So we don't have to read that. There's videos on YouTube. This is from people with real British accents from University of Nottingham. So if you want to watch it, you know, understand without my terrible British accent. So what does ISBN have to do with RAID? Well, obviously, if this is disk 0 or disk 1, disk 2, disk 3, disk 6, disk 5, instead of reconstructing a digit, we can reconstruct a single drive. We get a different sum check. Because we're multiplying by a different value at each point in there, right? Now we have a sum check where the calculations give us different results in the two different calculations. So when you have two different things, two different pieces failed, we can then calculate the partial sum using the simple parity, XOR parity, and we can calculate the sum using the grade 6 Reed-Solomon parity, and we can subtract one from the other and figure out what the data was on the two missing drives, right? So if two data drives, we just compare the XOR and the ISBN-like OR. Now, modulo 11 is not convenient for computers. Computers like to do everything in binary. So let's ask ourselves, can we use the power of 2? Well, here's our times table mod 8. Now, in order for it to work, we need to have a multiple inverse for every single number in our field. So what do you see here? 5 times 1 is 5. 5 times 2 is 10. Mod 8 is 2. 5 times 3, 15. Turns into 7. 4, 1, 6, 3. That looks good, right? Well, look at 4. 4 times 1 is 4. 4 times 2 is 8. Modulus 8 is 0. 4, 0, 4, 0. There's zeros in this table. And there's no ones on that row, right? This is not a Galois field. A Galois field is defined as a field where we have successfully built the table with an inverse on every multiple. That is a fully self-enclosed finite field. Évariste Galois, back in 1832, came up with a way to do these things not using prime numbers, but using powers of primes. He made major advances in this, sent them to a friend one night, said, I'm going to fight a duel the next day, probably the next day, and he got killed and shot in the stomach and died miserably in the duel. Famous stories of crazy mathematicians going out and getting shot and dying young, right? His most significant is, of course, he found out that, of course, integers mod p is a finite field where p is prime. Integers mod p to some power, p is prime, is a finite field if a proper primitive polynomial is chosen. So he came up with the concept of a primitive polynomial, a thing you could apply to your 2 to the power field. 2 to the power 3 of 8 is equal to 8. 2 to the power 4 is equal to 16. You could apply this primitive polynomial and make the divisors work. So we'll show you how that works. Now, other people would say his most famous contribution is a novel if there is no quintic. I don't know, whatever that means. So here's a timetable of Galois field 2 to the third, or size 8, with primitive polynomial x cubed plus x plus 1. So as long as I use this as my primitive polynomial, this is what my multiplication table looks like. 2, 4, 6, 3, 1, 7, 5, 3, 6, 5, 7, 4, 1, 2. Every row has everything on it. There is a 1 on every row, every column. The inverse of 2 is 5. The inverse of 3 is 6, so on and so forth. How did we do it? We used logarithms plus a primitive polynomial. So we're going to look at this one here. 4 times 4 is 6. Okay, we're going to remember that for now. So x times y, remember, is the anti-log of the log of x plus the log of y. Of course, we said in our very first lecture, 17 times 35 we can calculate by adding. We take log to the base 10 of 17, we get 1.2304. Log to the base 10 of 35, 1.5441. We add those numbers, we get 2.7745. We take the anti-log of that, or 10 raised to the power of 2.7745. We get 594.98, or approximately 595. This is how a slide rule worked. Anybody in here ever seen a slide rule? I'll have to bring it to next lecture then. I actually have one. When I was a kid, they used slide rules when I was very young. I remember when they came up with calculators, I was old enough to notice that these cool little weird things my dad used to mess around with were on sale for really cheap. So I went out and got myself a, slide rules were like iPhones. You'd pay hundreds of dollars for one of those things. And they had them for sale for like $5 or $10 because they were unloading the inventory because they knew no one is ever going to buy one of those again. So I actually got a slide rule for it's really cheap, and I kept it for a prop. I knew I'd need it for this class. Prescient little kid. I was, annoying as heck too. So building a multiplication table in Galois field. We choose a base prime. Computers prefer 2, we'll use 2. You can build using 3, 5, 7, right? Choose a number that is a power of the base, 4, 8, 16, 32. Choose a primitive polynomial. We'll figure out what that is later. We'll build a table of powers of that base, aka anti-logarithms. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, so on and so forth. And we then take that table, we read it backward to get the logarithms, and we then use powers and logarithms to build our multiplication table. Okay, so here we go. We'll choose our primitive polynomial. For GF of size 8, there are 2 primitive polynomials, x cubed plus x plus 1, x cubed plus x squared plus 1. Right? We take our base prime, 2. 2 cubed plus 2 to the power of 1 plus 1 is 8 plus 2 plus 1 is 11, or hexadecimal B, or binary 1011. 2 cubed plus 2 squared plus 1 is 8 plus 4 plus 1, or 13, or the letter hex D, or 1101b. Those are our two primitive polynomials. Okay? So all this is saying is take your primitive polynomial. If I had using as 3 as a base, I'd have 9 plus 3 plus 1, right? If I was using 5 as a base, it'd be what? 125 plus 5 plus 1, right? So we calculate our powers of 2 by multiplying by 2. The convenient thing about binary is all you have to do is shove everything left. You just stick a 0 on the least most bit and shove everything over, and you multiply by 2, right? And then if the result exceeds the size of your field, and your field can go from 0 to 7, so if your number gets bigger than 7, now you subtract it from the primitive polynomial. And in binary, of course, subtraction means we're XORing it. So we XOR it with the primitive polynomial, that brings it back in the range. So we're going to use 11 for our example, okay? So we'll start off, n is 0. 2 to the power 0 is 1. Any number to the power of 0 is 1, right? 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 8 is outside our field, so instead of taking it modulus 8, we're going to use a primitive polynomial. We're going to XOR 8 with a primitive polynomial, and that will bring it back into the field. But it won't bring it back in at 0. It'll bring it back in at 1, 0, 0, XOR 1, 0, 1, 1, or 3. I double 3. 2 to the power of 4, right, is 16. But I've doubled 3, so I actually have a 6, right? 2 to the power of 5, I'm going to take 6, I'm going to double it, I'm going to get 12. I'm out of range again, I XOR 12 with 11. 1, 1, 0, 0, XOR 1, 0, 1, 1 turns into a 7. I double 7, I get 14. I XOR that with 11, get 5. I double 5, I get 10. XOR that with 11, I get 1. That's already taken up here, right? Your finite field in a power of prime is not modulus the prime number, not modulus the number. It ends up being modulus 1 less than that. Now we've got our anti-logs, our powers, right? And all we have to do is read it backwards. So here's n and the anti-log of n. And how do I derive the logs? I simply reverse the labels. If 4 is the anti-log of 2, that means that 2 is the log of 4. Okay? And this obviously makes sense, right? I raise, anti-log and log are opposite operations. So going forward, we're going to do a format, we're going to use a 3-column table. N is the power that we are raising our number to, right? We are raising 2 to the power 0, 2 to the power 1. Come on, mouse, where'd you go? 2 to the power 2, so on. Now it says, I'm going to disappear on this screen because there we go. And on the right column, I'm going to say this is the anti-log. In the left column, I'm going to say this is the log. So you see tables like this from now on, log n, anti-log n, okay? Remember, when you're looking something up, you're starting in the middle, you're going either left to get the log, or you're going right to get the anti-log. What is a logarithm? Doesn't exist. 0 has no logarithm. It's negative infinity, right? So we're going to build our GF2 times 2 of Galois field of 8 table. So 4 times 4 is the anti-log of the log of 4 plus the log of 4. Log of 4, here's n. Log of 4 is 2, right? Add 2 plus 2. Let's go backwards again. Unchange the label. 2 plus 2 is 4. The anti-log of 4 is 6, right? In our little table here, I don't have 4 and 6 in the middle here, but you can see. So 2 plus 2 is 4. 4 times 4 is anti-log of 4 is equal to 6. So 12:30, 3:30. I guess we're not going to get to our next lecture. All right, so that was our introduction to finite field theory. Now, we're going to have a couple of examples here. And you see a lot of links here. It says unb.ca/Tervo, Galois field calculator, Galois field multiplication table, irreducible polynomials. Remember we talked about, we'll start with this one. Boop, boop, boop. It doesn't want to bring it up front. All right, here's our primitive polynomials. Remember I said in Galois field of size 3, 2 to the cubed, we had two primitive polynomials, 11 and 13, right? And there they are, 11 and 13. We go to size 16, where n is 15. We have two primitive polynomials, 19 and 25. We go to size of 31, we see 1, 2, 3, 4, 5, 6, 7 primitive polynomials. So depending on how big we want our field to be, whether it's going to be, you know, size 8, size 16, size 32, 64, 128, 256, right? We have all these different numbers that we can use. RAID subsystems use a Galois field of size 256 because that is conveniently enough exactly the size you need to store a single byte worth of data, 8 bits in a byte. So you can store 8 bits in there, right? Back to here. The next thing we can look at is, here's some multiplication tables. Galois field 2 to the 3 based on primitive polynomial 13. If I look at this one here using, sorry, 11. If I look at using 13, I get a different layout. All the same numbers are in there, they're just in different places. If I say to generate one using a big number, x to the 6th, you can see that this is generating a 64 by 64 table, right? And we'll fill that multiplication table all the way out from 1 to 63. And this is, of course, all in decimal. I can tell it to do it in hexadecimal, and I can tell it to make pretty colors. And it'll show me all the different things in there. This is more interesting if I look at it in addition table. I can build an additional table. And you can see that we get big old blocks of data that repeat over and over again with the colors. Okay. Here's a calculator. Galois field calculator. You give it two numbers that fit in your Galois field, and you can tell it to compute multiplication, addition, subtraction, and division. Here's course notes, which are worth looking at. On the top level of his course. And this is an engineering class that he taught here. And he's got a lot of stuff that we cover in here in much more detail, if you're interested in that sort of thing. And finally, over here is a paper where the person talks about how we recover errors using RAID 6, right? And he talks about, you've got your data drives, your P parity and your Q parity, calculates things, does the subtraction, so on and so forth. He actually has code at the bottom, which I have stolen and used in this class. Enough of that, enough of that. End of slides. All right. Cool. Any questions about finite field algebra? I'm going to recommend you go ahead and in your spare time, go ahead and download or download the slide deck or read it and look at those last links on there and see if you can try calculating for yourself. Go find a primitive polynomial and see if you can start calculating that log, anti-log table, and then try to do a mathematical formula on it. So I would stick with the smaller ones, 16 or less for now. And we'll do a homework about that later on. But for now, just kind of mess around with it as you find time around the homework that I've already assigned. All right. One more concept thing to mention is on the Hamming ENCODE homework. I had 3 people as of this morning that had not done anything. Again, that homework said to go to this spreadsheet, find your WSUID in column A. There were 3 people in the class who have not done it yet. So please try to get to that. You'll still get credit. It'll be late. Oops, that's not the right one. Hamming ENCODE. There we go. There's our spreadsheet right there. And again, the reminder to just code something up and put it out there. And if you don't, we'll assign you a number. That's okay. But if you want credit for that, we'll need to get that posted here as soon as you can. And I noticed this is point out that these homeworks are graded. These are not small homeworks, they're medium homeworks. They're not a full 25 points like the programming ones are going to be, but they are graded. So we're looking for you to do something, get it done. So if you're late, you're going to be starting to lose points, effective probably tomorrow, because it was just due yesterday. All right. There's that paper to read. We're done. Okay. Now we need to do, where am I here? Why am I here? That's right. Attendance. You know, I haven't looked at what this is. So those are online. I'm going to stop sharing so you don't get to see anymore. Stop recording.